So let's cover the overall 4 steps that it takes for active potential to occur. The first one is resting membrane potential, and as you could see that our waves or our charge is about 70 millivolts, and that's called resting membrane potential. There's going to be some event to go ahead and depolarize. So we're going to go back to a positive charge in this event, and that's going to make an action occur. We're going to have to repolarize, which means we have to go back to having those positive and negative charges on both sides of the cell, which always makes it slightly more negative until we get back to our resting potential. So let's talk about how these occur. I envision on your exam you're going to see a chart just like this. You're going to have to draw one just like this. And I might ask you what all the events that happen in resting membrane potential are all the events that occurs in depolarization, repolarization, or hyper. So be prepared, and as we go through it, go ahead and I would even stop the video, print this out, and just take notes as to everything that happens at each of these events. And make sure you know before the exam. I can imagine it being a big question, mostly because I'm writing the exam. So, resting membrane potential, if you go back and think about it, these are where those charges are going to be on both sides of the plasma membrane. It turns out the inside of the cell is going to have a slightly negative charge, and the outside of the cell is going to have a slightly positive charge. And what happens is this is called the resting membrane potential. This is not the current, because the current would be when they start to move around, but this is our potential energy that can get some work to occur. So resting membrane potential, or RMP, is found in all cells. It's really important in neural and muscle fibers, but this happens in your liver and your kidney and all over the place. But we're really going to just sort of sit and think about just that neural, and then maybe we'll come back to that muscle junction later. But basically what happens at resting membrane potential, we're somewhere around 70 to 90 millivolts, and the cell could be excitable, but right now we're just in this sort of charge state where it's going to be slightly negative inside the cell and slightly positive outside the cell, and really no current is moving from one side to the other. But resting membrane potential occurs because sodium is on the outside, potassium is on the inside, and there's pumps that keep sodium concentration high on the outside and pumps that keep that potassium inside. And we have to keep those separated. There's a lot of calcium that sort of leaks out a little bit, but because there's those charges that attract them, they keep coming back because the inside of the cell is negative. And the reason why it's negative is not because of the potassium. It's negative because these large proteins are in the cell and they all carry a negative charge, and it really attracts potassium back. Sodium really wants to get in the cell, but these channels only allow potassium to come in, and that's it. And that basically keeps us at our resting potential, where there's a ton of potassium inside the cell and a ton of sodium outside the cell, and something has to open to basically let these guys in. Right now, those gated channels, and there's, remember, the ligand gated channels, the voltage gated channels, and the sodium potassium channels, they're all closed, they're inactive. So, quick recap. Inside the cell, there's a high amount of potassium. Negatively charged particles, those proteins are going to be in there. On the outside, there's going to be a high amount of sodium. And there's also going to be some chlorides, but not enough to do anything. So why is sodium more concentrated outside and potassium more concentrated inside? The answer would be there's a sodium-potassium pump, and we're going to do an activity in class that will sort of bring back why there's so much sodium on the outside and so much potassium on the inside. So resting membrane potential, potassium will have these channels that are always open. So potassium could potentially leak to the outside, but again, they're so attracted to that negative charge that they come right back. Also, there's a pump that requires energy called the sodium-potassium pump, and it's always set up to allow potassium in and sodium sodium out. But potassium is drawn backwards to that negative charge, so that's why we sort of stay at that resting membrane potential. So at resting membrane potential, a few sodium leak into the channel. Some sodiums are going to leak into the cell, but we can pump them right out, and that's still going to make us somewhere at that 70 millivolts. The next thing is we're going to do depolarization. So depolarization means that we have some charge that's saying that the cell needs to carry that electrical signal into the cell. So we need to do some voltage exchange. And remember, voltage was one of those currents are going to go from, the current is basically where we have one side of the cell and the other side of the cell, one's positive, one's negative, and now there's going to be this depolarization event that occurs to get some of those ions into the cell, and that's going to create a more positive internal environment, and that's what we're doing here. How do we do that? The easiest way to do it is have that sodium start to come inside the cell. So those sodium channels are opened. There's a few ways they could be opened. We'll talk about them soon. And then when sodium diffuses down a concentration gradient, remember they're at high concentration to low, so they want to go to the other side of the membrane, but they're not allowed because the lipid bilayer is in the way. But now that we've opened up a gate, the sodium rushes to the other side. And because they're rushing to the other side, we're starting to create a slightly positive charge. And as that positive charge gets more and more and more positive, around when we get to 30 millivolts, we're going to call that our depolarization event. And that's going to cause that electrical energy to sort of move. We have to now repolarize that event because we can't keep going positive, positive, positive. And how would we repolarize? Meaning that we have to get the sodiums out and the potassiums in. And how we're going to do that is by those gated sodium channels have to close. If we don't close them, sodium's just going to keep rushing in. The voltage gated potassium channels open, which means that potassium's going to start to diffuse out of the cell because they're going from high to low. And also, remember how they were attracted to the negative charge? Now that we're slightly positive here, they're going to go to the other side. So now really it's just going to be simple diffusion that moves them across. And now the cell, as they start to leave, starts to become more negative, and the cell is going to become minus 70 millivolts. Actually, it becomes even lower than that. So here would be 70. We're going to be in this thing called a hyperpolarization, which means it's even more negative. So if you look, we're probably in the 90 millivolt range. So it's called hyperpolarization, which means that we've got to go ahead and get these ions back on the right side. And how we're going to do that is, remember how number one, we have the potassium now has gone to the outside. We're going to have to let them come in. And we're going to have to go ahead and try to get the cell more negative to go back to that resting potential. And how we're going to do that is those voltage gated potassium channels have to close, so they can't go on the outside anymore. These special pumps, sodium potassium pumps, are going to be activated with ATP, and what's going to happen is the potassium is going to start to come back into the cell, and it's also going to push out that sodium. So potassium back in, sodium back out, and slowly what's going to happen is we're going to go back to that resting membrane potential. So this is the kind of thing that I want you to spit out for my exam. So for number 1, if I say what's going on in resting membrane potential, I want you to tell me that it's at 70 millivolts. The potential energy is the cell is waiting to be stimulated. Sodium-potassium pumps are actively transporting sodium out of the cell and potassium into the cell. And potassium is diffusing out slightly. For depolarization, gated sodium channels are open. Those sodiums are going to diffuse down a concentration gradient into the cell. The inside of the cell becomes less negative and more positive, and that's why we're seeing this energy uptick. We're going to be at 30 plus 30 millivolts. Finally, what's going to happen is we have to repolarize. We have to get everybody back on the other side. And how we're going to do that is we're going to have a change in voltage that's going to stimulate these voltage-gated potassium channels to open, and potassium will diffuse out of the cell. Those are also going to go ahead and shut that sodium from coming in the cell. Now we're at hyperpolarization, so we're going to be even more negative than we really need to be. We're going to be maybe at minus 90 millivolts, excuse me. So it takes time for the potassium gates to close, and that's going to create a slightly more negative response, and then finally we're going to go back to resting membrane potential.